Dear physics aspirants, right now I have the moment of force torque. The figure perpendicular to the plane containing RNF and its direction is given in the right-handed screw rule. Screw rule of right-handed, and you will see here the theta angle and r sine theta based on the right-handed screw rule. Moment of force torque. We have learned that the motion of a rigid body in general is a combination of rotation and translation. If the body is fixed at a point or along a line, it has only rotational motion. Fixed at a point, you will see here. Based on the rotational motion, we know that force is needed to change the translational state of a body, i.e. to produce linear acceleration, linear fixed point. We may then ask, what is the analog of force in the case of rotational motion? To look into the question in a concrete situation, let us stop the example of opening or closing or a door, because based on the fixed point rotational motion, door is working on the fixed point rotational motion. A door is a rigid body which can rotate about a fixed vertical axis, passing through the hinges. You know what makes the door rotate. It is clear that unless a force is applied, the door does not rotate. But when a force does not do the job, a force applied to the hinge line cannot produce any rotation at all, whereas the force of given magnitude applied at right angle to the door, its outer edge is most effective in producing rotation. Right angles, it is not the force alone, but how and where the force is applied is important in rotational motion. The rotational analog of force in linear motion is moment of force. The rotational analog of force in linear motion is moment of force. It is also referred to as torque or couple. We shall use the word moment of force and torque interchangeably. We shall first define the moment of force for the special case of a single particle. Later on, we shall extend the concept of systems of particles, including rigid bodies. We shall also rotate it to a change in the state of rotational motion, i.e. angular acceleration of rigid body. Figure will provide you the understanding R into F. Here you will see the sign given here, and R into F. R, here is the R, and if a force acts on a single particle at a point P whose position with respect to the origin O as given in the position vector R. R is the vector bold sign. 7.18 will provide you the information that the moment of the force acting on the particle with the respect of the origin O, defined as vector product. This is a symbol of vector product R into F. The moment of force or torque is a vector quantity, because direction, we have the direction, the symbol T, small t, like this stands for the Greek letter tau. This is tau. Tau is equal to R into F, Greek letter, Greek symbol, and the magnitude of tau is the tau into RF sine theta to a 7.24. Figure to a 7.24 will provide you. Now, where R is the magnitude of the position vector I, R, i.e. the length of P. R is the magnitude of the position vector R. R and R with the bold sign and the simple sign. OP. F is the magnitude of force F, and theta is the angle between R and F. R and F, and the theta F is the magnitude. Edge on moment of force has dimensions ml squared t minus 2. Its dimensions are same as those of work or energy. It is however a very different physical quantities than work. Moment of force is a vector, while work is a scalar. Work hasn't direction. So the scalar of the SI unit of moment of force of is Newton meter nm, and the magnitude of the moment of force may be petrogen. Tau is equal to r sine theta f. R perpendicular f, or tau is equal to rf sine theta is equal to rf perpendicular, where r perpendicular r sine theta is the perpendicular distance of the line of action of f, and the origin and the f perpendicular is f sine theta is component of f in the direction perpendicular to r. Origin f1 perpendicular component f in the direction perpendicular, and note that tau is equal to 0 if r0 f0 and theta is equal to 0 degree or 180 degree. Here you will see this figure will provide you the information, and here you can see if the line of action of the force passes through the origin. One may note that force since r into f is a vector product per page. Properties of a vector product of two vectors apply on it if the direction f is reversed. The direction of the moment of force is reversed if directions of both r and f are reversed. The direction of the moment of force remains the same. Properties are here. In the next video I will provide you angular momentum of a particle. Till then, thank you.